All right, let's look at some graphs. So this lecture is on 1.6, and 1.6 is graphs of functions. Okay, so a couple things that we're going to look at in this section. The first thing that I want to look at when it comes to functions is what I call the base functions and the idea, or the base graphs. And the idea behind these guys is that as we progress in this class, but then also as you go into calculus, if you remember these graphs like the snap of your finger, so you see the function and you know what the graph looks like, it's going to make your life that much easier. If you have to really think about what does that graph look like, then the class is going to be moving ahead and you're still wondering what the graph looks like. So these base graphs are going to be the guys that you kind of want to commit to memory, base graphs. And the way that we're going to do them right now is, I'm not really going to plot too many points. These are more sketches just to, again, to put into your memory bank so that you have an idea of what they look like. So the first base graph that we're going to use is f of x equals x. Okay, f of x equals x. And this guy, whenever you see this function, this is your diagonal line. And I'll give my graphing a little bit of a break. It's not going to be perfect. But f of x equals x is the diagonal line. So anytime you see that one, that diagonal line should pop in your head. And the more that can happen, the easier life is going to be on you. Okay, so there's our first base graph. The second one, we're going to bump right up. We're going to see f of x is equal to x squared. Now again, depending on how many algebra classes you've taken to this point, this one might already be in your brain. Whenever you see x squared, this guy is going to be your basic parabola. So it's going to be the parabola that looks like this. Should be symmetrical, but again, it's just a sketch. And it should have this point on it, 0, 0, and this guy is called the vertex. Okay, so your base graph has a vertex at 0, 0, and is a parabola opening up. Okay, so then the next one that we'll look at would be x cubed. Again, another little sketch going on here. Now, x squared is all positive because when you square things, the answer is positive. X cubed is somewhat similar to x squared, except that it can be negative. So what it looks like is half down in the negative section and half in the positive section. And it's a little bit steeper than this guy over here. Still goes through 0, 0. Notice all of these guys go through 0, 0. All right, so we've got our first 3 there. Now, as I'm not using too much of the board, I'm gonna have to go back and erase. So the next guy that, let's see, you may not use this guy too much actually, but it's a good graph to know. Well, maybe there are a fair number of word problems. I'm thinking about calculus, and you might actually use this guy. So now we're looking at f of x equals the absolute value of x. So this one is going to be another one that's all going to be positive. It's going to be above the axis. But instead of being like the parabola, this one looks like the V. Okay. Again, still at that 0, 0, but a V rather than a parabola. Alrighty. Then 2 more, and that's, oh no, 3 more, sorry, 3 more. The next one is going to be another one that we see this function quite a bit. So the square root of x, Okay, so f of x is the square root of x. And the square root of x looks like this. Again, it starts at 0, 0, but this guy is going to grow this way. Okay. So there's the square root of x. And notice that all of these guys that we've drawn, if you run a vertical line down through any one of them, okay, they are all functions, okay? Everything we've drawn here is a function, so we definitely have functions going on. Okie dokie, so there's the square root of x. Then, if we can do the square root of x, we should be able to do the cube root of x. So if f of x is the cube root of x, and now if you don't trust me and you think I'm just messing with you, you can always plot x, y points to graph these guys, but you will see that the sketch I'm giving you is the actual graph that we've got. This is what the cube root of x looks like. So the cube root of x. Okay. And then one more. And the last one, definitely one that you will see, this is 1 over x. Okay, 1 over x. And because it's a fraction, this guy does look a bit different. So first off, there's going to be this boundary line running right down the middle. And this boundary line is called an asymptote. And we'll talk a lot more about asymptotes when we get into chapter 2 or 3, I think. But just for right now, you can go with asymptote. What the 1 over the square, or 1 over x looks like is these two arcs. And they fit into their two separate quadrants. Okay, so two arcs, and they kind of hug in there like that. Okay, now I know that was quick, but those graphs, as we continue on, those are the guys we're going to use, and the quicker that you can just look at it and go, oh, square root of x, that's the arc. 1 over x, oh, those are those two arcs going on. Absolute value of x, that's the v. That's basically where you want to get to. Okay, so base graphs to start us off with. Then the other thing, or the next thing that we want to look at is if we are given the graph of a function, can we tell what the domain is? So checking domain, but from a graph. We talked about domain a number of times, but what if I gave you a graph? So what if, and this is just going to be some weirdo graph, okay? Nothing, not one of our base graphs or anything. Let's go 1, 2, 3, 4. 1, 2, 3, 4. I guess the y-axis doesn't really matter. So let's say that we started here, and then we went like that. Okay, so like I said, just some weirdo looking little graph that we've got going on there. And we want to know what the domain is. So now remember that the domain is going to be the x values. So we're looking from left to right. So from left to right, what we're looking for is what is the first value that's getting used. And there's an ending, or it comes to a point here. So as we come along this way, the first value that's actually getting used on the x-axis is this -4, isn't it? So as we come this way, -4 is getting used. And we're going to write this in interval notation. So if we're using -4, it means we're going to put a bracket on it. And then we keep going this way, and we notice that all these values are being used until we get to, remember, x-axis, -1. But -1 also has a closed-in circle, so it is getting used. So we'll hit it with a bracket. Now, we're going to use that union notation because we're going to combine. Now, is any of the values between here getting used? No. So we're making a jump up to where x is equal to 0, also with a bracket. But now, as we go this way, what does that arrow imply? Are we stopping at 4? And we're not. The arrow implies that it just is going to keep going and going and going. So the arrow implies that we're headed to infinity. So this end had an actual boundary, okay? So that's why we started at -4. But anytime that you have arrows on there, that's telling you you're going to go to either positive infinity or negative infinity, depending on how we see it. So one more of these just for the heck of it, just to say we did it. Okay, so let's say this time we have a graph that looks like this, comes up here. So another weird one, okay, so I'm making them weird so you actually have to kind of really think about this. So now this time, again, interested in the domain, not so interested in the range right now, not a big deal there. But now always left to right, but left to right, we've got this arrow that's way out there. So all of these values are getting used off to that side, which means that we're starting at negative infinity. And then we're moving left to right, we're coming up, we're coming up, we're coming up, we're coming up, and we end right here, what looks like -2. But with that open circle, it means that we're not including the -2, so we're going to hit that with a parenthesis. Now we'll union that, and we then, again, there's a break or a skip here, so we're going to start again at -1, including, and all of these values are getting used, getting used, getting used, getting used until we get to +1. But the +1 is not going to be including, okay? So it's an open circle, so we've got a parenthesis. That one looks a little weird. And then we got something weird going on here. Now there's no interval left over. There's just a value at +2. So we're just going to say 2. And then it skips, and then there's another value at +3. Now remember, we don't care this way what's going on, just this way. So there was a point here, so we put 2. There's another point here, so we put 3. And that's it, that's all we've got, so we're done. So that one had a couple intervals in it, but then it also actually just had numerical values. Okay, so they're gonna show you some weird drawings like that. That's what you're looking for. Then, let's see what's next in this one. Oh, we need to look at piecewise functions. Now, a couple sections ago, we talked about piecewise functions, and now we're going to do some graphing with piecewise functions. So graphing piecewise functions. Now, if you remember back, a piecewise function is a function that has multiple parts. So we might see one, let's say, we'll name this guy h of x, that looks like this. It says that it's absolute value of x if x is less than 0, and it's x squared if x is greater than 0. So it's got 2 parts, 2 functions, and then it also has 2 intervals, or 2 kind of domain issues there. And again, we're using those base graphs that we just talked about, using those base graphs here to, and then we're going to use those both together to create kind of a funny looking graph, very similar to what we were doing right here. So let's say we've got our XY graph here. Now remember, we're thinking when we see absolute value, we're thinking that's the V. So we're thinking about the v. I'm just going to sketch it in here. It's easy for me to erase, so you don't worry about this right now, but just sketch it in there. But this says that I only want to use the v where x is less than 0. So that means the v is not getting used at all over here. It's just getting used on that side. So this is the only part of the v that we want. We don't want this side of the v. Once we're on this side of the graph where x is greater than 0, then we're looking at x squared. And x squared is not the v, it's the parabola. So again, you can think of the fact that we've got like a parabola, there's the whole parabola, but we don't want this side, we only want that side, right? So we're gonna come down here and then we're gonna turn around and make our arc of our parabola going up. So straight here and then arced on that side. But then we also have one other spot that we have to pay attention to, and that is what's going on right at 0. This says that we're looking at the v when we're less than 0, we're looking at the parabola when we're greater than 0, but in this particular case, is anything happening at 0? And it's not. The way I wrote this, there's nothing happening right at 0. So the way that we show that is by putting an open circle. Okay. All right, so let's look at another one. Let's say that we want to use, let's say we'll call this g of x. And this one I'm going to make a little bit more difficult. Actually, I think I'm going to have 3 parts here. Make it a little bit longer. Okay, so I want us to use 2x if x is less than 1. I want us to use 6 if x equals 1. And I want us to use the square root of x if x is greater than 1. Okie dokie. So a little bit more to this one. Now the first part that makes this ugly is that instead of starting at 0, instead of having your boundary or your changeover at 0, I've put it off kilter a little bit. So there's actually the change happening here instead. And when that happens, sometimes it's a little bit harder to figure out. So if we want to know where 2x is right here at this boundary, then we can take, oops, I almost went on the board where it's not recording. So then we can take 2x and plug in 1. So if we go 2 times 1, it equals 2. So if we're here at 1, this equals 2. But it's not actually equal because it's not including. So instead of putting a closed-in circle, I'm going to put an open circle there. And now 2x is just a way of writing a line, right? It's a line with a slope of 2. So that would be up 2 over 1. But we don't want to go up 2 over 1 this way because this line is getting used on this side, right? So what we need to do is go down 2, backwards 1. So the 2x is getting used over here. So we'll go from our open circle down 2 over 1, and we end up with a line that looks like that, going downhill. The second part says that when x is equal to 1, right where we are, the answer is 6. Okay, well, right where we are, we could go up 6, 3, 4, 5, didn't leave myself enough space, 6. And we just put a spot, or a point, not a spot, a point. So there we are there. Okay. And then this says when x is greater than 1, we're going to use the square root of x. So now again, if we want to know where the square root of x is at 1, we can come over here and say square root of x, plug in 1, so we get the square root of 1, which equals 1. So, so at our boundary here, we're actually going to be at 1, but it's also going to be an open circle because it's not including. And now remember that the way that the square root of x looks is it looked like this arc, like that, right? So using our base graph, the square root of x looks like an arc, but we don't want this part of it, do we? We only want the part that's above 1 or greater than 1. So we're looking at an arc like that. So less than 1, you've got this line headed in that direction, then you got this random point, and then you come back and you have an arc. And that's how we use piecewise functions to draw basically very weird looking graphs. Okay, but now we can do that. All right. Okay, so there's one more thing in 1.6 we have to do, but I gotta take a break for a minute, so we'll leave this here and then I'll finish up 1.6 in a couple minutes, okay? All right, thank you.